Dusen or Dusen?
Dusen.
Dusenberry.
If you see how it's spelled, you basically just pronounce the S with a Z. So Dusenberry.
Okay, Dusenberry, Mike.
Yep.
Mike.
Yep.
Okay, maybe it's just Mike. I will put the full name. Okay, so I'm here with Mike. You're working for IBM in the Spark Technology Center.
Absolutely.
And we are here at the OpenTech AI conference in Helsinki.
Mm-hmm.
And you have done a tutorial on mitosis object detection.
Yes.
And do you want to tell us about your work in the Spark Technology Center and then especially about your little project about the mitosis detection?
Yeah,
Okay.
certainly. Yeah. So I work as a machine learning engineer in IBM's Spark Technology Center.
Okay.
And so the group overall focuses on open source machine learning
Mhm.
and distributed computing. And so we have like lots of interests, and particularly, it originally started out focused on Spark, which
Mhm.
does cover that kind of spectrum. Personally, I focus on machine learning side of it. I'm particularly interested in the mathematical aspects of machine learning,
Mhm.
as well as certain particular types of application areas. And in particular, I'm interested in medicine as an area of application.
Okay. So you are a medical doctor or you try to be one or something, no?
No, so I studied computer science in undergrad,
Uh-huh.
and I love computer science, but ended up getting interested in medicine,
Mhm.
and decided to attend medical school.
Okay.
And while I was in medical school, I started working on a machine learning project applied to a particular medical problem. And kind of through that experience, I decided that I felt like I could contribute more if I were to switch focus and concentrate on machine learning primarily applied to medicine rather than medicine with machine learning on the side.
Mhm.
So I ended up leaving medical school, leaving medicine, and I came out to California and joined IBM to start working on machine learning projects and focusing on medical applications.
I see. Okay. So what are your top 3 tools you're using all day long?
So I think in machine learning, I want to think first and foremost on the math, right? So the actual
Okay.
mathematical components. How do you define a problem, and how do you define it mathematically?
Mhm.
But then tools actually can help that. It can help you have very clean, tested implementations of that. And so once you understand the math, then you can rise up in the abstraction level slightly. So tool-wise, I tend to use the Python as a language.
Mhm.
If it's basic machine learning or just basic matrix manipulation or tensor manipulation more generally, I'll use NumPy.
Mhm.
But I really like the area of machine learning, which we kind of call deep learning, which is really just about learning models directly from raw data, and rather than say having a greater level of human involvement and trying to think deeply about types of features and then feeding that to a simpler model.
Mhm.
So I think about deep learning a lot, and as part of that, I make use of TensorFlow a lot. I also use PyTorch, and I've used Keras as well on top of TensorFlow.
Okay. Yeah, so I'm a Keras guy because
Yeah.
I'm not so much in the medical field.
Sure.
And then I just so as of now I never had the problem that I cannot express something in Keras that I had to use TensorFlow. Did you
Sure.
have that problem before?
So interesting. I started with Keras. I started with Keras several years ago prior to TensorFlow. So this was sitting on top of Theano. Particularly the medical research project I worked on during med school, I ended up using Keras. And
Mhm.
Keras is a fantastic library. I particularly like to think of it as having kind of two aspects. And
Mhm.
one is this great API for defining a model,
Yeah.
right? And then the other part of the API is the actual training loop or learning algorithm itself via methods on a given model known as like fit or predict or these other types of things, and that gives you great expressivity. But over time, I started working more and more. Got to the point where there were some things that I wanted to do that were difficult to do in Keras, and particularly started thinking about things like special types of metrics,
Mhm.
and metrics I wanted to do in real time, such as
Mhm.
like online streaming type of fashion.
Ah, okay.
I wanted to get data input faster
Mhm.
because I would have these big models that take a long time to train, and I have these fancy GPUs to use. But if you don't have fast enough data input, then you can actually starve those GPUs. And I tried using the buffered image generators in
Mhm.
Keras. Ultimately, it was hard to keep up with the GPU. And so, if you move down to TensorFlow, you do have great APIs, particularly the TF data package, which used to be in Contrib and is now a top-level package. Great, simple, and you can plug it in directly with the rest of your TensorFlow graph. But what I've moved to actually is having a kind of hybrid approach where I still define my models using the Keras API because kind of the layers or function-based approach is quite nice. But then with Keras, you can, if you have that model, you can feed in a standard TensorFlow tensor, run it through the model, and then pull out a tensor at the end and use that tensor in the rest of your TensorFlow graph.
Oh,
And so if you have particular metrics or particular data input pipelines, you can add that. And then probably the most important thing I added is I had a problem when I was working on this mitosis detection project where I wanted to try a hypothesis of making use of a pre-trained model. So in other words, trying to use transfer learning because I didn't have a lot of data, but I felt like having a more complex model would be useful for this type of problem. So the idea is, try to make use of a pre-trained model that was trained on a very large data set, particularly ImageNet, and then pull it over and fine-tune it to this particular problem. And so when you do that, you end up ripping off the end of an existing model that would maybe classify it into some number of classes that were based on the number of classes in the original data set. In this case, 1,000 classes based on ImageNet. And you rip that off, and you place your own classifier at the top. And that classifier would classify into the number of classes for your new problem. So for my problem, it was a single item, and it was a binary problem, yes or no. And so once you do that, then you have most of the model is pre-trained, and you have this very new piece at the end. And so you could train all the way through that, but because that new classifier at the end, basically it's just another weight matrix, is random, you could end up having very high gradients to earlier layers, and you'd rather not destroy those. And so it's helpful to first freeze those layers and train just this new classifier. And then once that's trained, then go through and slowly fine-tune the rest of the model. And so that kind of involves like multiple optimizers and maybe like a slightly custom training loop that I found to be easier to express in TensorFlow. Not to say you absolutely can't in Keras, but I found that a little bit easier.
Okay. Are you freezing the other layers completely and then you just open up the valve a bit, or how is that working?
Yeah, sure. So when you train that new classifier, you do freeze everything else, and you train just that new classifier. When I say classifier, it's very general because it could be a single function, just single weight matrix, so like a dense layer, right? Or it could be multiple. You could add whatever you want on top. You freeze everything else, meaning, and by freezing, it's just you don't compute gradients or you just don't do updates. And that depends on your implementation. In this particular case, I actually go through and filter out which variables I'd like to update. It's in TensorFlow and I have access to that. And then I directly optimize just the variables from the new classifier. Then when it comes to unfreezing, it's a good question. Like, do you completely unfreeze layers? Do you just slowly do it? I found it easier just to completely unfreeze some number of layers and then train through that, but train very slowly. And while you could train a new classifier with something like a fancier algorithm, like Atom or RMSProp or something, you tend to want to use something like just plain stochastic gradient descent with some type of momentum, like a Nesterov momentum, and then train it slowly. And slowly here just means having a very low or small learning rate. And then the number of layers that you actually unfreeze is going to be based on your model's performance on some validation data set. And so if you find that you unfreeze several layers and it's overfitting, then you might be allowing too much complexity to be changed. You may want to refreeze several. So the better way to do it is just to slowly start with one layer, unfreeze it, see how well your performance does. Then try the whole thing again with 2 layers. Or 3 functions, so on and so forth. Just kind of experiment with different numbers, and it kind of depends on how much data you have and how much you can really ask of your data.
And the same holds if you want to choose how much from the original model you throw away and how much you keep, no?
Yeah, so that's a good point too. A lot of times I just would end up ripping off the final classifier. However, it's a good point because if you have, say, a ResNet 50, it's a great pre-trained model. It's easily available in Keras. That basically has a bunch of convolutions and residual blocks, which we won't talk about. But you end up with a final kind of like average pooling layer and then a single dense layer, and that's actually what classifies it into 1,000
So
classes.
that's 1,000 softmax something.
Yeah, and so
Yeah.
really you could just rip that off. You could experiment with ripping more like residual layers, but really just rip that off. Or say like a VGG 16, another kind of classic one now. It has a series of convolutions and max pooling, and then it has 3 dense functions at the end. So you can imagine just ripping off the very last one and placing your own. But I actually found it very beneficial to rip off all of those dense layers because there's some prior literature that found that those are not necessarily useful, or not useful, but they're not necessary. And if you rip them off completely and just add a single dense layer, you can actually get a much faster implementation.
Okay.
But yeah, in general though, you can imagine going back further and ripping more and more off because you might worry that later functions in a model might be too tailored to a particular data set that it was trained on.
Okay. So I see transfer learning some sort of art or science on its own, no?
Yeah, it is a little bit of both.
Okay. And are you going to open source this model for us, or is it?
Yeah, so part of where I work, it's on open source, and personally, I heavily believe in open source data and open source code, but more generally, open source research. And so this code actually is already open source.
Okay.
So it's online. We'll put a link up.
Yeah, I will put a link in the description.
Yeah,
Good.
yeah.
Okay.
And with soon, it's still an active project, but the plan is, as soon as I am able to kind of reach some level of success that I feel comfortable with, is to actually release a trained model as well.
Okay.
So the goal, this could be used as a medical model that could then be used for transfer learning to other medical data sets.
Oh, I see.
So that's kind of the plan.
Cool. Okay. So you told me you are working for the Spark Technology Center. So where's Spark in all this?
Sure. So, Spark Technology Center, we started out very heavily involved with Spark. And, Spark has machine learning, it's got distributed computing. For this particular project, though, it's focused more on the deep learning aspect. And so I'm mainly using TensorFlow for it. However, there is an interesting angle where, for mitosis detection, to get a little bit more specifics, you have this piece of tumor tissue that you've placed under a microscope and taken a photo of, basically. And you're told where individual cells are dividing, so individual cell mitoses. Images are large, very small objects. There could be many approaches, but there's some prior literature where they actually cut it up into several small patches and then trained large deep neural nets on those individual patches. The idea would be, given a patch, yes or no as to whether or not this patch contains a cellular mitosis. So you train a model like that, right? But that's not necessarily the ultimate goal. The ultimate goal is to be given a full-size image and have the model tell you exactly the XY coordinates of the centers of each mitosis.
Oh, okay.
Right? So then you're left with a single. Once you have the model, if you take this approach and you like this approach, and there's other approaches, like, more of an object detection type of approach, maybe an RCNN or YOLO or something. If you like this approach, you'd have this trained model, and then there's still a prediction stage. And so the prediction stage is not particularly interesting. You're just going to try to chop these big images up, or whatever you get, apply your model to each one, and then kind of post-process that to transfer the binary prediction on each patch back into kind of a map of the overall image and the probabilities everywhere of whether or not a given location has a mitosis.
Okay.
So it's really, you want to just apply this model to as many places as you can as fast as possible. And so we had an intern, his name was Feihu, that actually wrote up a Spark job to actually run this prediction in parallel on a GPU cluster.
Okay.
And so he wrote kind of a GPU manager for this problem, and because of the fact that I wrote the code such that the model definition was in Keras, I can actually save the Keras model, or save the model out as a Keras format, even though the training is actually in TensorFlow. And so then I can hand this Keras model over, and he can make easy use of this predict function. And so essentially this code ended up being a Spark job where we have this big data set, we map that out, and of course the data set lives on these different machines, and then we send out a job with the model to make predictions in each location, and then we pull that all back together into basically big prediction maps.
Okay.
So it's an interesting case of using Spark in a clever, nice way, particularly for a just parallel or embarrassingly parallel type of problem.
Okay. By the way, I don't know if you know, I'm running this Coursera course
Sure.
coursera.org/learn/AI.
Yeah.
And in week 4, I'm using Deep Learning for J and
Okay.
SystemML
Okay.
for reading the Keras models and putting that on Spark.
Oh, very
also.
nice. Very
It's
nice.
also working quite nice.
Very nice. That's awesome.
Okay, cool. So, thanks a lot.
Oh,
And
awesome.
let's go back to the conference.
Sounds good.
Okay.
Thanks.